At first, there's nothing unusual about the star. For millions, sometimes billions of years, it burns in the darkness, converting hydrogen into light and holding itself together through a delicate balance. Gravity pulls inward while energy pushes outward. Between these opposing forces, the star survives, but eventually its fuel begins to run out. The outward pressure weakens. Gravity gains the advantage. In a fraction of a cosmic heartbeat, the star's core collapses while its outer layers explode into space with unimaginable violence. What remains may become something from which neither matter nor light can escape: a black hole. Black holes are often described as cosmic monsters, objects that wander through space, consuming everything in their path. But they are not empty holes, and they do not behave like giant vacuum cleaners. From a safe distance, a black hole's gravity is no different from that of any other object with the same mass. The danger begins when something moves too close. Surrounding every black hole is an invisible boundary called the event horizon. It is not a physical surface. There is no wall to touch and no warning signal announcing that it has been crossed. It is simply the point beyond which escape becomes impossible. Outside this boundary, a spacecraft could still fire its engines and retreat. Inside it, every possible path leads deeper into darkness. Even light, the fastest thing in the universe, cannot return. Imagine approaching a black hole in a spacecraft. At first, the journey might appear strangely peaceful. The black hole itself would be invisible, revealed only by the way it bends the stars behind it. Their light would curve into distorted rings and arcs, creating a warped window into the universe. But closer to the event horizon, the calm would begin to disappear. If the black hole were actively feeding, it could be surrounded by an accretion disk, a vast whirlpool of gas, dust, and shattered matter. As this material spiraled inward, friction and magnetic turbulence would heat it to millions of degrees. The disk could shine brighter than entire galaxies, flooding the surrounding space with lethal radiation. Powerful magnetic fields might also launch narrow jets of particles from the region around the black hole. These beams can travel across thousands of light years, carrying extraordinary energy into the darkness. Yet the most disturbing effects would be caused by gravity itself. A black hole's gravitational pull becomes stronger as you approach it. If you fell toward a relatively small black hole feet first, your feet would be pulled far more strongly than your head. Your body would stretch lengthwise while being compressed from the sides. Scientists call this process spaghettification. It sounds almost humorous. It would be anything but. Long before reaching the center, the difference in gravity across your body could tear apart your bones, organs, cells, and eventually the atoms from which you are made. But a supermassive black hole would offer a more deceptive journey. These giants, found in the centers of most large galaxies, can contain millions or billions of times the mass of the Sun. Their event horizons are enormous, and the gravitational difference at the boundary can be surprisingly gentle. You might cross the event horizon without feeling anything at all. There would be no sudden impact, no flash of light, no physical barrier, but the universe behind you would already be gone forever. To a distant observer, something even stranger would seem to happen. As you approach the event horizon, your movement would appear to slow. Your light would become redder, dimmer, and increasingly stretched by gravity. You would seem to freeze near the boundary before fading from sight. From your perspective, however, time would continue normally. You would fall onward, unaware of the eternity you appeared to leave behind, and somewhere ahead would be the singularity. According to general relativity, the matter inside a black hole continues collapsing toward a region of seemingly infinite density. At this point, our familiar laws of physics stop producing meaningful answers. Space and time become distorted beyond anything we can currently describe. The singularity may truly exist, or it may be a warning that our theories are incomplete. To understand what lies there, we would need to unite Einstein's description of gravity with quantum mechanics, the theory governing the smallest structures in nature. For generations, physicists have tried to build that connection. So far, no complete, experimentally confirmed answer has emerged. The mystery grows darker when we ask what happens to information. If you burn a book, its words appear to be destroyed. But in principle, the information remains encoded in the heat, light, smoke, and ash. The universe changes form, yet the details of its past are never completely erased. A black hole appears to threaten that rule. When matter falls through the event horizon, the information it carries seems to vanish from the observable universe. And through a quantum process known as Hawking radiation, a black hole may lose energy over an almost unimaginable span of time and eventually evaporate. If the black hole disappears completely, where does the information go? Is it destroyed? Is it hidden within the radiation? Or does it survive somewhere beyond the event horizon, sealed away from our universe? This is the black hole information paradox, and it challenges our deepest understanding of reality. Black holes are not merely destroyers. They shape galaxies, influence the environments where stars are born, and may have played a central role in building the universe we see today. At the heart of our own Milky Way sits Sagittarius, a star, a supermassive black hole roughly 4 million times the mass of the Sun. It is not hunting us, but it is there, silent, ancient, and concealed within the crowded center of our galaxy. Across the cosmos, countless other black holes remain invisible. Some are dormant remnants of dead stars. Others are giants feeding in distant galaxies. A few may drift alone through interstellar space, detectable only when their gravity briefly bends the light of something behind them. We can observe their shadows. We can measure the motion of stars around them. We can even detect gravitational waves created when two black holes collide. But we cannot see what lies beyond their horizons. Every black hole hides part of the universe from the rest of existence. Behind that boundary, every future-directed path points inward, toward a place where our equations fail and every message becomes trapped. Perhaps the singularity contains nothing more than crushed matter and the final consequences of gravity. Perhaps it conceals a new state of space and time. Or perhaps black holes are not endings at all. Somewhere beyond the last visible light, the answers may still exist, falling endlessly through the dark, preserved inside objects that the universe created, and then made impossible to question.